we're going to carry on from where we were yesterday, which was the amount of substances topic. It comes under the physical chemistry topic in A-level chemistry. So yesterday we looked at relative molecular mass, relative atomic mass, balanced equations, empirical formula, molecular formula, and the ideal gas equation. So we're going to look at today percentage yield and atom economy, and then work through some exam questions to sort of show how these questions are embedded into these equations are embedded into questions, so that it's not just this clear sort of processing that you're sort of normally used to. It's about step up to A level. So percentage yield is basically how much product are we getting at the end of a reaction. So percentage yield, you would usually expect it to be less than 100%. It's usually not 100%, and there's quite a few reasons why. So that's what we're going to look at now, is why it's less than 100, and why you would usually expect, if you're doing a percentage yield calculation, for your percentage yield to be less than 100. Realistically, we want our percentage yield to be as close to 100 as possible, within limitations and reasons, because obviously the more yield we get, the better. But we'll look into the nuances of that in a moment. So usually less than 100. One reason that percentage yield can usually be less than 100 is due to something called an incomplete reaction. So this is either a reaction that's very slow, or it's a reaction that's not given enough time to fully react. That can sort of mean the same thing, but for example, if you're doing a reaction, carrying something out, and you end it too soon, you've not given it enough time to fully react, you won't get 100% percentage yield. Very, very slow reactions, you'll end up actually with an incomplete reaction, because to wait for it to fully react can take a very long time. And some reactions, their rate of reactions will slow as different limiting factors are used up. So incomplete reactions can be due to slow reactions or reactions that aren't given enough time to fully react. But we also have reversible reactions, and that's obviously, if we don't stop a reversible reaction at the right point, what can actually happen then is some of our products can start to turn back into reactants, so the reaction starts to reverse itself. So unless we know that point and stop it at exactly the right time, some of those products will start to turn back into reactants. So both of these reasons are a reason behind incomplete reactions. And incomplete reactions, they reduce your percentage yield. They're going to make sure that your percentage yield is less than 100. So one reason why someone might have a percentage yield that's less than 100 is because they've had a slow reaction, not given reaction enough time to fully react, or it's a reversible reaction that has now started to reverse itself. Another reason we can have a low percentage yield than 100 is because of side reactions. So what can end up happening is sometimes our intended product is not created at all, and we can end up creating different products than what we intended to. This is more happening with experimental chemistry, and you're intending to create a specific product. What you don't realise is actually you're making a different product because this side reaction is happening at the same time. So that will reduce yield. Saying it reduces yield is probably a little bit nice, because basically it can reduce your yield to 0. You could have a side reaction where you do make a little bit of a product that you're intending, but most of the product that you start to make isn't what you intended to make. You start making unintended products, so your percentage yield again will be less than 100. A third thing that can affect your percentage yield is extraction. So extraction is all just about actually getting that product. So the percentage yield is how much usable product have we got from this reaction that's taken place. It's really hard to separate some products from the reaction mixtures. It's especially hard to separate 100% of your product from your reaction mixture. So let's surmise that we've had a reaction where all intended products are made. It wasn't a slow reaction, it wasn't a reversible reaction. You gave it the exact amount of time, but actually some of them are really hard to separate from a reaction mixture. Some things will have to go through things like electrolysis, some things will go through filtration, crystallization. It's that extraction process can be really hard. An example for this from a biochemical aspect is monoclonal antibodies. So when scientists are making monoclonal antibodies, we have to purify them, and it's really, really hard. It's really, really hard to extract them and purify them. So that extraction process isn't just necessarily actually being able to get the product on its own, it's purifying it to get rid of anything extra that we definitely 100% don't want. So that will reduce the yield. And extraction is really important. It's not something that can be sort of ignored, because in that aspect, that they're monoclonal antibodies that we could be using in humans. Anything that we use in medicine, they have to have a very, very high purity rate. So to get to that, we will actually end up wasting some of our product as well. So because it's hard to separate it from the mixture, if we have some reaction mixture that's on some, we can't get rid of it, we can't purify it properly, we have to then get rid of that part of the product, because we can't use it because it's not pure. In a similar manner, but yet different, we have waste. So we use the term glassware, but basically any equipment. Some product will remain stuck to glassware or equipment. Using the idea even of extraction, the different ways that you may need to extract your product, you might actually be able to extract it 100%, but because you're transferring it from one different piece of equipment to another, you're going to lose product there. It's going to stick to your glassware. You can't get 100% of your product off your glassware. If you were, you would have to use often different substances to help you get it off the glassware, and that will then render your product not pure and not usable. So again, that would reduce your yield. One that affects your yield but in the opposite way is hydration. So water is really, really hard to fully remove from a product. So if you have got a product that is that has occurred in the presence of water, to actually remove that water, that's really, really hard. So hydration of your product can cause a percentage yield above 100%. So if you're ever doing calculations for percentage yield and you find out, oh, hang on, this is actually above 100, double check it first to make sure you haven't done something wrong. Then if it's not, and it is over 100, it will be due to hydration. And that's quite a typical exam question that could come up where you're asked to calculate percentage yield and then you might be asked, suggest why this is the given percentage yield. Well, for example, if it's over 100, it can be due to hydration. So yeah, percentage yield, we sort of want to get it as high as possible, but we have that sort of word of sort in there. And we'll look at that when we get onto the next topic of atom economy. And it's all sort of a balancing act, because actually to get our percentage yield as high as possible, it might take us more time and cost us more money than if we had it a little bit lower. And so it's that balancing act of actually, if I only got a 70% percentage yield, but it only cost me £100 and it only took me 1 hour, I could get a 90% percentage yield, but it takes me 5 hours to do that and it costs me £600. It's that weighing up the cost. Which one is more cost effective? Is it the lower yield and repeating the process multiple times, or is it the higher yield but we get less product being made in that time? So that's where the ideas come into it behind. So percentage yield, you can be asked to calculate percentage yield. So percentage yield we calculate with our real yield divided by our theoretical yield and multiplied by 100. So our real yield, that is the mass of a desired product from a reaction. And the desired product is the correct part there. It is not the mass of for all the products that are made. We will get lots of different products often being made in a chemical reaction, but it's our desired product that we need. So it's the mass of that. Our theoretical yield is our maximum mass of a product that could possibly be created from a reaction. We can calculate this as a balanced symbol equation if a mass of reactants is known. So if we know a mass of reactants, we can do use the idea of a balanced symbol equation, use the ratios. Well, if I've got this many moles of this, I've got this many moles of that. That means I'll have this many moles in the end. You can convert that into a mass. So if we had a set amount and we know what we're working with, we can calculate from a balanced symbol equation a mass of reactants, a mass of our product, sorry, from the given mass of reactants using the conservation theory of conservation of energy and conservation of mass theory. The idea that we're not going with conservation of mass, we're not going to lose any mass, we're not going to gain any mass. So using that theoretical procedure, that would be our possible maximum mass, regardless of waste, hydration, extraction, speed. I don't want to say speed, I've forgotten what the word is for it though. Incomplete reactions and side reactions. So aside from them, that would be our 100%, that would be whatever. So our theoretical yield is our 100% yield. It's how much we could actually get. But we do that obviously in mass. So real yield is a mass, theoretical yield is a mass, divide them by each other, multiply 100, and you will get your percentage yield. So an example for percentage yield, feeling like this is percentage yield. Yes, this is an example of a question that will come up in percentage yield section of the exam. Now, when you first look at it, it's not actually super clear where percentage yield actually comes into this and what's happening, because we end up getting asked quite a lot of questions around this. So, for example, you have been asked here, suggest a student wishes to collect hydrogen involved from a reaction between magnesium and hydrochloric acid. I can't see this corner bit. They add 1.2 grams of magnesium ribbon to 30 cubic centimeters of a 1.5 mole solution of hydrochloric acid. Suggest how a student might collect the hydrogen evolved and measure the volume. So the idea is that actually we're just talking about our practical skills. These aren't taught explicitly now at A level, so there is required practicals, which I will send links over in videos. Now, required practicals for A level, you don't have to, they're very similar to GCSE, so you don't actually have to have carried them out, but you have to know the process of them, the method of them, how you would carry them out, what correct equipment you would use, and then they can come up in exams. So I'll send you, when we come across them at different points, different other YouTube links to them. They would be more useful for me sat explaining them, because you'll be able to see somebody doing the experiment. And then what will often happen is you get given a question like this and you're asked, suggest how a student might collect the hydrogen that's been evolved and measure the volume. So actually you're using lots of your information from GCSE, lots of your knowledge from GCSE, and lots of your knowledge from A level to answer this question, but lots of it is just extracting basic knowledge from GCSE. So we would conduct our reaction in a conical flask. We are mixing magnesium and hydrochloric acid together. So it's magnesium ribbon with hydrochloric acid. We want a conical flask. We would want a conical flask because of the shape of it. And we don't want just an open flask, because we're wanting to collect hydrogen. Hydrogen is a gas that we're going to want to collect. Conical flasks are great because we can add a bung to the top that would stop the gas from escaping. Not going to be able to measure the hydrogen if we just trap it in there. So we actually want to collect it and measure it. So something you'll have seen quite a lot before is gas syringes. So what you can do is, if you have the reaction taking place in a conical flask, you can add a bung to the flask. The bung can get connected to a gas syringe, and therefore the syringe will allow the volume of gas to be measured. You can do some other strange things. I'm using the word strange because you can do it where you have a reaction taking place, but rather than using a gas syringe, you can have a bucket of water, You still have it in a conical flask with a bung in, but then you have a tube coming out the top rather than a gas syringe being attached to the bung. This tube then goes into this bucket of water where you have a upturned measuring cylinder which has some water in, and then you basically, as the gas fills up the measuring cylinder, you record the displacement of the water, and then through that you can then work out the volume of it. What would actually often happen is you'd end up doing that sort of experiment in a lab rather than a gas syringe, because most schools and colleges don't have many gas syringes. The better way is using a gas syringe. They often don't let you use gas syringes at school or college because they can often get a bit damp. When they get damp, if people aren't watching them carefully, because obviously they're being used with reactions that do contain aqueous solutions. If they get damp, they don't necessarily work properly, and then it can break them. So they don't often like people using them. So you come up with these like crazy other different versions of measuring volumes of gas, where actually this sort of question will suffice. But I will show you, I'll send you later an example of both the experiment being done in both those different ways to show you how they work. Gas syringes are also expensive. So often schools don't have many. They're also made of glass, so they're breakable, so they often end up breaking a lot. So again, a bucket of water and a measuring cylinder, conical flask, bung, and a delivery tube. Schools and colleges have a lot more of them, they're a lot cheaper. It does the same thing, just one isn't as precise or refined as the other. So that was the beginning of the question. So suggest how we might collect the gas and measure its volume. Then the question continues. So recap the beginning of the question. So, oops, I don't want to do that. A student wishes to collect hydrogen evolved from a reaction between magnesium and hydrochloric acid. They add 1.2 milligrams of magnesium ribbon to 30 cubic centimeters of a 1.5 mole solution of hydrochloric acid. You are then asked to calculate the percentage yield of hydrogen given that 400 cubic centimeters was collected in the syringe and the AR of magnesium is 24. So, oh, no, I haven't written that on. So we'll go through this now. So looking at that, we've got 1.2 grams of magnesium ribbon. So our percentage yield would be our actual yield divided by our theoretical yield. So to get to that point, what we have to do is this. I've lost my, where is my answer? Work it out as we go. So we have got, so our percentage yield equation would be, let me get my pen working. Draw, find mass, NH2, magnesium ribbon. Okay, so we have got, so percentage yield is calculated like this. So we have our actual yield, and it's going to get divided by our theoretical, and then it is going to be times by 100. So what we're going to do is we're going to need that balanced symbol equation from the beginning. So we would want to rewrite our balanced symbol equation out again. So I'm just going to pop a balanced symbol equation here. So it was magnesium, which is a solid at this point, and it was with 2 moles of hydrochloric acid, which is an aqueous solution, and it becomes magnesium chloride, which again is an aqueous solution, and hydrogen gas, H2 gas. Okay, so what we need to do first is we've got our actual amount of magnesium we've added, but we need to work out our yield, our percentage yield. So we've collected 400 cubic centimeters in the syringe, but we need to work out our theoretical yield first. So let's delete our equation for the moment and we'll come back to that. So the first thing we need to do is we need to work out what the theoretical yield would be. So like I said earlier, if we know our balanced equation, we can calculate our theoretical yield. So the first thing we need to do then is we need to calculate the moles of all of our reactants. So we're going to calculate the moles of magnesium first. So we're going to work out the moles of magnesium. So moles, again, a reminder, is mass over relative molecular mass. The mass of magnesium is 1.2 grams. So we're going to do 1.2 grams, and we are going to divide that by its relative molecular mass, which is 24. So that will give us 0.05 moles. We then need to work out our moles of hydrochloric acid. So moles down again. This time it's HCl. This time, hydrochloric acid, we have hydrochloric acid not in mass, with it being a solution. It's in, we've got its concentration and we've got its volume. So we know its concentration is 1.5 moles. So we're going to use the concentration times by volume to give us moles this time. We're going to use this equation. So again, it's a percentage yield question, but we're actually using the two different mole equations to work out our theoretical yield to then do our percentage yield. So you can see it's a multi-step process. So we're going to do concentration multiplied by volume to give us the moles for hydrochloric acid. So our concentration is 1.5 moles per decimeter cubed. I'm going to multiply that by, well, this is another thing that we had talked about yesterday. We've got 30 cubic centimeters. If we think back to our standard SI units, everything needs to be the same. Everything needs to be in the same unit. So we've got 1.5 moles per decimeter cubed here. So we need to convert 30 cubic centimeters into decimeter cubed, which would give us 0.03 decimeters cubed volume of hydrochloric acid. Multiply those two together and we would get 0.045 moles. So we've got our moles for magnesium and our moles for hydrochloric acid. Now we're going to look at which reactant is limiting. Well, our limiting reactant is our reactant that's less, that we don't have in excess. So our limiting reaction is hydrochloric acid. So limiting is, oops, what happened there? Limiting is hydrochloric acid. And we're going to calculate now the moles of hydrogen we have at the end. And we're going to use our ratio of hydrochloric acid to hydrogen. So if we have a look here, so our ratio of hydrochloric acid to hydrogen, well, we've got 2 moles of hydrochloric acid. We've got 1 mole of hydrogen there. So it's got a ratio of 2 to 1. So the 2 to 1 ratio means we've got for every 2 moles of hydrochloric acid, we produce 1 mole of hydrogen. So let's put 1 mole there. So finally, to work out our moles of H2, work out moles of hydrogen, actually how many we've got. So that's our ratio is 2 to 1. We want our moles of hydrochloric acid, and we're going to multiply that by 0.5. And let me talk you through that. So we're going to have our moles of hydrochloric acid. We use our moles of hydrochloric acid because this is our limiting factor. So we're going to multiply that. And we're going to multiply that by 0.5 because it's a ratio of 2 to 1. Therefore, we have half the amount of hydrogen moles of hydrogen as we do moles of hydrochloric acid. So we are going to multiply the moles of hydrochloric acid by 0.5. Our moles of hydrochloric acid, as we can see up here, are 0.045. So we've got 0.045. I'm going to multiply that by 0.5. And that would give us a final answer of 0.025 0.25 moles. That's not our final answer, but that gives us our moles to get onto our next part of the question. So we now need to calculate the volume of gas that we produced. So to work out our percentage yield, we need to do a few things. So we need our actual divided by our theoretical. We haven't actually got there yet with our theoretical. So to get there finally, we now need to calculate the volume of gas that we produced, because our percentage yield is based on our volume, not on the amount of moles. So finally, we need to calculate the volume of gas. So the volume of H2 that we're going to produce, and that is our moles of H2, and it's going to be multiplied by 24, and that's obviously because that is our relative molecular mass, our relative atomic mass. So moles multiplied by 24, we're going to do 0.0225 multiplied by 24, and that will equal 0.54 decimeters cubed. So calculate the percentage yield of hydrogen given that 400 cubic centimeters was collected. This is in decimeters, so we need to turn this into cubic centimeters. So we've got 540 cubic centimeters. This is our theoretical yield. We got there eventually. So now we can do our percentage yield calculation. From here, we want to put our actual yield. I'm going to change pen colour so you can see what I'm doing now, actually. So we want to get our actual yield, which is 400 cubic centimeters, which we can see here. That is our actual yield. Divide that by our theoretical yield, which is 540, times that answer by 100, and that will give us a theoretical yield of 74.074%. Round that to one significant figure, and we've got 74.1%. So that is our percentage yield of 74.1%. So you can see how this looks like a very simple question, percentage yield. Oh yeah, actual divided by theoretical. But actually in reality, it's a multi-step process where we've had to work out the moles of both reactants. We've had to work out which one is the limiting factor. Then we've had to work out our ratios. Then we've had to work out our moles of hydrogen. Therefore, from our moles of hydrogen, we've been able to work out volume of hydrogen. And then from our volume of hydrogen, we've finally got our theoretical yield. So then we can work out our percentage yield. So it is a very complex multi-step process. And that is one of the most complex ones. So let's have a look now at atom economy. So atom economy. Atom economy is this equation. It's quite a nice equation. So atom economy is a percentage again, and it's the relative molecular mass of our products divided by our total relative molecular mass of all reactants. Now, it's relative molecular mass of our products, of our desired products, divided by our total relative molecular mass of all reactants, then times by 100. So if atom economy is 50% and the relative molecular mass of all products is 6, what is the relative molecular mass of all the reactants? Well, you could rearrange this equation. So if we substitute in our values to the equation as it is, we would have, we would have, we would have 50 equals, well, 50% equals relative molecular mass of products is 6 divided by our total molecular mass. So put our MR reactants there. Rearrange that equation. So our MR of all our reactions would be 12 grams per mole. And obviously, if our atom economy is 50%, and our products is 6, we just need to double the 6, because we know originally all our reactants had double the amount because it's been halved. So our atom economy would be 12 grams per mole. So reaction pathways. Why is this not working? Reaction pathways. Reaction pathways are different ways that we can choose to go depending on basically atom economy. So atom economy and percentage yield works together, and we basically want to get as high a possible atom economy as we can, but whilst looking into other matters. So reaction pathways, cost. We want the smallest amount of reactants saves money. So the least amount of reactants we can have, the cheaper our reaction is. So the cheaper the products would be. Obviously, we have a ratio issue of, oh, well, if we have this much and that much, we can make double the amount of product, but this is on the idea as we want to have the smallest amount of reactants as possible. So we need to work out the minimum amount of reactants needed for that reaction to take place to make that desired theoretical quantity of our final product. Because we don't want anything in excess. If we've got anything in excess in our reactants, in a huge amount of excess, it's pointless because it's not going to react and we haven't used it and it just costs us money. Waste. Higher atom economy means less waste is produced. So we're making exactly what we are required to make, making less side products. Percentage yield is involved again in here. So actually how much are we actually getting? How much are we actually producing compared to what theoretically we would think we would produce? And the usefulness of our byproducts. So some byproducts that we will make can actually be really useful. So our atom economy can be quite high. So if we make a reaction, going through a reaction and we get 2 products, we have our desired product that the whole point of our reaction is for. But if we make a useful byproduct, well, actually, even if as a company we don't use it, we can sell it on to somebody else, or we can use it maybe in another one of our reactions. If it is just waste, then we have to get rid of that and it hasn't made anybody any money. So actually useful byproducts can offset some of these issues. Our position of our equilibrium is also really important. So like when we were saying incomplete reactions, we need to know what that position of equilibrium is. And that's really, really important so that we know the exact mass and the exact quantity, so we know when to stop our reactions for our rate of equilibria. And then our rate of reaction is really, really important as well. Obviously, as we know, we can increase the rate of reaction by increasing temperature, by adding catalysts, by changing the amount of reactants that we have. However, does that offset the cost of doing that? And so this is all the idea of reaction pathways. So what we're going to spend the next 20 minutes sort of looking at is just a few different examples of different questions that can come up for the whole of this sort of topic of amounts of substances. And we'll sort of start off with these more basic, clearer ones, and then go on to a few more complicated ones. So chlorine exists as 2 isotopes. Chlorine exists as the isotopes 35Cl and has 75% abundance, and it also exists as 37Cl and has a 25% abundance. So what is the relative atomic mass of chlorine? Well, we want to recall that equation from before. So obviously our equation from before to work out relative atomic mass, our AR, is AR equals mass times charge ratio times by abundance over, total abundance. So in this situation, we have 35, so that is our mass charge ratio. We've got 35 and its abundance is 75, so we're going to do 35 times by 75. And we're going to add to that 37, chlorine 37, 25% abundance, 25. I'm going to get all them. Our total abundance is 100%. Divide them together. And if we popped them into a calculator, what we would find is we would get the answer of 35.5. So our relative atomic mass of chlorine is 35.5. These questions often come up with mass spectrometry questions, so you can be given an image of a mass spec and you're asked to calculate these. Lots of people don't bother showing this bottom part and just do the top part. I'm not saying that's necessarily the right thing to do, because if you're being asked to show your equations, show your processing, you should be including your total abundance. There could be a rare occasion that the total abundance is 100. It should always be 100, but you can get odd, rare occasions. And that's our first example. You can then get questions like this. I'm saying this, I can't get it to work. How many moles of carbon-12 are there in 1 gram of carbon-12? So it's a mole question. Mass over relative molecular mass will give us how many moles of something is there. Well, we've got 1. We know its relative molecular mass is 12. Well, actually, we don't need to change that. That's our answer. It's 1/12. So we've got 1/12. And actually, we know that because when we've talked about moles before, 1 mole is equivalent of 1/12 of a carbon-12 atom. So again, if we have 1 gram of carbon-12, 1 gram is equivalent to 1 mole. Therefore, we've got 1/12 of a carbon-12 atom. Empirical formula now. So what is the empirical formula of C4H7O2? So this is our molecular formula. Remembering empirical formula is the discard. I don't know what's happening. Zoom's disappeared actually. Meeting controls. What's happened? What's happened? I'm not quite sure how long that's been paused for. I think this is all working again. I don't know what I clicked on. I think everything is now working again. Who actually knows? I don't, that's for sure. Files. Right, let's carry on, and hopefully this is working again. I'm not really quite sure what I did then. Okay, so yeah, empirical formula is the simplest way that we can show molecular formula. So it's always, molecular formula is always a multiple of the empirical formula. So it's the simplest ratio we can get of a molecular formula. So the empirical formula is C4H7O2. Well, actually, the empirical formula of this is C4H7O2. We can't do anything to make this any simpler, mainly because we've got H7 in here. If we started trying to make it any simpler, we'd end up with something like C2H3.501. And we don't deal with decimals when we're using numbers like that in this way. It just doesn't work. So actually, the simplest way of showing the molecular formula of C4H7O2 is C4H7O2. So that's clear there. So now going into a bit more complicated questions again. So a student has a solution of blue hydrated, I'm going to underline the word hydrated because that's really important in the word blue actually. So we've got blue hydrated copper sulfate. The student wants to obtain pure hydrated copper sulfate. We get suggest a method that the student could use to obtain pure dry hydrated copper sulfate from the solution. Again, this is like the question from before where you're getting asked to give a method, you're recalling basic methods from chemistry and from before. So it's not necessarily something that you have specifically learned as in, this is a specific example, this is specific practical, you need to know this method. It's actually, well, I want to make copper sulfate. We know copper sulfate's a crystal. How am I going to make this? Okay, well, I'm going to use the method crystallization. Because we know that is the method that we would use to get those crystals. So from that, we go through a suggested method to get there. So we would say we would filter. Oh, why is this not working? Here we go. So the first step, if we think back to crystallization, we're going to filter out any of the insoluble solids to get out. So filter out any insoluble solids. Then step 2, we are going to heat the solution to boiling point. And this is where it'd be good to mention equipment again. So we're going to heat using a Bunsen burner and have everything on a tripod and gauze. And we're going to heat the solution in an evaporating basin. And we're going to heat the solution to boiling point until half the liquid has evaporated. Evaporated. Then stage 3, we're going to let the liquid cool. So we're going to cool the solution, and we're going to leave it over time to evaporate. So the rest of the liquid can evaporate. And then step 4, what we should be left with is blue crystals, which we remove from the dish, and then we will pat dry using a cloth or tea towel to remove any excess water. So that would be the first question, part of this question, because actually lots comes from these questions. They like to do them as multi-step questions. So suggest the method. So we've done that. We've suggested the method there. Then you get asked, okay, why is only half the water evaporated initially? Okay, so let's look back at the original question. Why are we going to evaporate half the water? Well, we're being asked to produce a solution of blue hydrate, not a solution. We're being asked to produce pure hydrated copper sulfate. Now, hydrated copper sulfate is the important word here, so let's type that down. So we're being asked to produce hydrated copper sulfate. That means water is present still in the copper sulfate, so it should contain water. If we evaporated off all the water when we were boiling it, straight away there would be no water left. It wouldn't be hydrated. So what we would get is, if we boiled off all the water initially, initially we would actually produce anhydrous copper sulfate. If we produce anhydrous copper sulfate, you can know that if you do that because it becomes a white crystal, and so that isn't pure hydrated copper sulfate because it's white precipitate. So then we think, okay, so we've got this bit of the question. Where is it going to go next? Then it comes on with some maths. So you get asked, let's move that down there. The student forms 2.56 grams of the hydrated salt. They then reheat the crystals until constant mass, and the mass of the crystals decreases by 31.25%. Use this information to calculate the value for X in CuSO4 X H2O. So basically, we're finding out how much H2O is needed. So we're going to actually look at our change in mass to start off with. The first thing you're going to want to do is calculate your change in mass. So our change in mass is we've got 0.3125. That is how much it is decreased by. So we're going to multiply that by the amount of crystals that we started off with, our mass to begin with, which was 2.56. So our change in mass is 0.8 grams. So that's our first part. So we've got a change in mass of 0.8 grams. So we need to now calculate our final mass. So if we start off with 2.56 grams, we're going to take away 0.8 grams, which would give us 1.76 grams. So our final weight, our final mass of the crystals is 1.76 grams. Now we want to calculate our water mass before heating. If we go and have a look here at our equation, our water mass before heating is going to be 0.8 grams. How do we know it's 0.8 grams? Well, because our change, so let me pop that here. So our H2O mass before heating is 0.8 grams. It's 0.8 grams because if our change in mass is 0.8 and all we have done to this reaction is heated it, therefore we know that then the mass that was left, the mass that we've lost must have been the water, so the mass of the water before heating is 0.8 grams. So then we need to work out what our mass of copper sulfate is. Well, we know what our copper sulfate mass is before heating, by the end, sorry. Our copper sulfate mass is CuSO4 mass is 1.76 grams. Now we want to go on to work calculating our moles. So we want to work out our moles of copper sulfate. So moles of CuSO4. Well, we're going to take our mass, 1.76, and we're going to divide it by our relative molecular mass. To work out our relative molecular mass, we are going to do 64. We've got one lot of sulfur, so it's going to be 32. 64 plus 32, this is to work out our AR, multiplied plus, 16 multiplied by 4. And that should give us, add them all together, 160. So our relative molecular mass, the copper sulfate is 160. To work out our moles, we're going to do 1.76, which is our mass, divided by our relative molecular mass, 160, which will give us moles of 0.011 moles. Now we're going to work out our moles of water. I'm just going to swap colours for a second. So we're going to do moles of water, moles of H2O. So we're going to go the same process again. Well, our mass of H2O is 0.8. Our relative molecular mass of water is 16 for oxygen, 1 for hydrogen, got 2 hydrogen, so it's 18. So it's 0.8 divided by 18, which will give us 0.044 moles. Then we can look at our ratio. So our ratio clearly here, we've got a 1:4 ratio. If we look at them, we've got 0.011, 0.044. So our ratio is 1 mole of copper sulfate to 4 moles of water. So then what we're going to go and put in front of wastewater per copper sulfate is 4. So it would be 4 here. So the number X there would be 4. And so X would become 4. So that would work out our balance symbol equation there, and that would be 4. I'm going to do one more, and then we will leave it there for today. So next example is question 2. So a student heats calcium nitrate crystals, causing the following reaction. The student collects the gas that is released. What type of reaction is this? So again, you're pulling from that general chemistry knowledge that you have, and the type of reaction we've got going on here is thermal decomposition. My pen isn't working again. Oh, it's multiple colours. Here we go. So thermal decomposition. We're heating something, and it's breaking the bond, so we're getting 2 new products. So it's thermal decomposition. Therefore, if we're heating something for a reaction to take place, is it exo or endothermic? Well, it's an endothermic reaction. Then we move on to the next set of questions around this. So then you're asked, okay, so calculate the volume of gas that would be collected if the student heated 1.312 grams of CaNO32 at 25 degrees Celsius and 100 kilopascals. Give your answer in decimeters cubed to 3 significant figures. So the first thing we're going to need is we're going to need to write out our equation. So we had our equation there, but let's just write it out again here so we can use it again. So it was, oops, pop it here. It was 2 CaNO32, 2 CaNO32, and that goes to 2 CaO plus 4 NO2 plus O2. Okay, so first thing we want to work out is our moles of CaNO32. So let's pop that here. We're going to work out our moles of calcium. So we're going to do mass over relative molecular mass again. Okay, so our mass, we're being told here is we've got 40 for calcium. So we're going to do mass R again. So we've got 40 and sorry, that's relative molecular mass. Let me rub something out. So our mass is 1.1. Where 1.1's come from? 1.312. So we've got 1.312 grams, and we're going to divide that by our MR. So I'm going to calculate our MR over here quickly so you can see where I'm coming from. So we've got 40, and we're going to add that to 14 times 2 because we've got 2 lots of nitrogen, and we're going to add that to 16 times 3 because we've got 3 lots of oxygen, but we've got 3 lots of oxygen 2 times by 2. Well, that equals 4 us. My bad handwriting, so I can't actually tell if that was 100. I think it's 164. I'm just going to have to double check now. 40 plus 14 times 2 plus 16 times 3 times 2, yeah, 164. That serves me right for having really poor handwriting. So 164. So that'll give us our moles. So 1.312 divided by 164 will give us 0.008 moles. Then we want to work out our ratios. So we look at the equation. Okay, so we've got a ratio of 2, 4, 1. Ratio of 2, 4, 1. 2 lots of calcium oxide, 4 lots of nitrogen oxide, and 1 lot of oxygen. We've got a ratio of 2, 4, 1. So therefore, we've got moles here, and here we know our ratio is 2 as well. So we know 2 is 0.008. Therefore, 4 moles, we're just going to double that, would give us 0.016. 1 mole, half of 0.008 will give us 0.004. So we've got a total amount of gas, volume of gas of 0.02 moles of gas. that is the amount of gas we have produced as our products. Now we need to calculate our volume of gas. So we're going to use our ideal gas equation. So that is PV equals nRT. We want to rearrange that because we want volume. So V equals nRT over P. So let's put in all our numbers. So N is our number of moles. Well, our number of moles is 0.02. So 0.02 moles. We're going to times that by our gas constant. Our gas constant is 8.31. We're going to multiply that by our temperature. Now, temperature in this question has been given in Celsius, 25 degrees, and we need it in Kelvin. Conversion unit for Celsius to Kelvin is plus 273.15. So it's whatever your degree Celsius is. So your degree Celsius plus 273.15. So our Kelvin is 298. We're going to divide that by our pressure, which is 100 kilopascals, but we want that in just pascals, which is 100,000 pascals. Therefore, our answer is 0.000495 cubic meters. We've been asked to put it into decimeters. So our final step is converting that to decimeters. So I'm just going to do that here in this gap and do it in a different colour just so we can see it. So our final answer would be 0.495 decimeters cubed. So you can see we've got a really complex multi-step process here to get there. So I'm going to leave that there for today. What I will do is, I can't find what I'm doing.